Okay, AP Stats. This is 10.6, Unit 10 over chi-square inference. This is a sixth discussion topic, which goes over nothing new other than combining everything that we've already seen. And I don't think I'm going to be going over everything in this. So this is a handout I was planning on printing out for you guys, and we're doing this together in class. Now, there were several of these things that, well, I think I would only do a few of these in class, and then have you finish the rest off on your own. Actually, no, it's been revised. But there were some extra set of instructions on here which were for homework, and it was based off of these particular problems. And this was used as a review handout. So we'll start off with the instructions for each of these problems. So for each of the following, letter A, identify the appropriate chi-square test, which is the main goal behind this particular video is to get you guys to be able to identify the proper test in either of these situations. There are three ways this can go. So there are three ways: goodness of fit, homogeneity, and then there's association / independence. Same test. So which is it? And a lot of the times you can look at the data right away and maybe come up with a good guess. So we'll look at number one. So number one, that's a contingency table. And we would imagine there being a table total. So it's not going to be goodness of fit. So right off the bat, if I see two-dimensional data, it's more than likely not going to be goodness of fit. But then we might be mistaken. That's why you want to read the actual problem itself, because it could be, does the distribution for men fit the distribution for women? It could still be goodness of fit. So if we're not actually given sample data for both and only one of them is like a model distribution, then that's going to be goodness of fit. So if it's a single sample, there's a model distribution that's already posited as a status quo. So there's some distribution out there that we're trying to check to see if this particular single population matches. So does it have the same distribution as this previously established population? So let's see, does a pollster's gender have an effect on poll responses by men? So poll responses by men. So I think men are the interviewees, and then we're talking about the gender of the interviewer, right? So the one giving the poll. So in a U.S. News and World Report article about polls, it was stated that on sensitive issues, people tend to give acceptable rather than honest responses. So their answers may depend on the gender or race of the interviewer. So what do we call that type of bias again? Or what do we call this situation? That's called response bias. So responses are going to be different some way, somehow. So if there is going to be difference in responses in actual opinion or reality, we call that response bias. So that's wittingly changing your response. So that's response bias. Another name for it's actually a blanket term for other types of biases that are similar to this, measurement bias. There's something wrong with our measurement tool, and we're not getting the proper measurements. So this is a type of measurement bias. There are other types of measurement bias. Like a wording bias is under the blanket of measurement biases. So we might not have intentionally inaccurate responses. The inaccuracy of responses might have been caused by something else, in this case, the wording of the question. So the question was misleading or narrowed down to certain, narrowed the options down quite a bit based off of the nature of the wording. So it's a type of measurement bias. In this case, this is intentional inaccurate responses. That's called response bias. So make sure you remember that. We'll be reviewing that stuff again later. So let's see. To support the claim, data were provided for an Eagleton Institute poll in which surveyed men were asked if they agreed with this statement: abortion is a private matter that should be left to the woman to decide without government intervention. So let's see. Male interviewers were instructed to obtain 800 responses from male subjects, and female interviews, and I think that should be interviewers, were instructed to obtain 400 responses from male subjects. Test the claim that the proportion of agree versus disagree responses, so those two categories, So men who agree versus men who disagree. So test the claim that the proportions of those categories are the same for the subjects interviewed by men and subjects interviewed by women. So is there a difference in the way they respond depending on the gender of the interviewee or the interviewer, sorry. And it looks like they are. Huge disparity here. Yeah, but anyway, what type of test? Part A. So identify the appropriate chi-square test. So is this goodness of fit like we were saying earlier? So the first type that we looked at was goodness of fit. Goodness of fit says, oh, the US population looks like this with respect to this variable. Does this one particular region fit the same distribution? That's not what they're asking here. So we don't have some single distribution that we're testing a single population by. So no, it's not a goodness of fit. So in a goodness of fit, and I might want to write this over here, for the most part, goodness of fit has one sample, one variable. So if you want to think statistically, single sample, single variable. Very, very important. So that's not the case here. We do have a single sample, I believe, or was it? So male interviewers were instructed to obtain 800 responses. So, oh, I see. These are two different samples, it looks like. So if I read this carefully, these are supposed to add up to 800. So we have a man interviewer, and he was instructed to get 800 responses. And then we have a different interview session given by a female, and these are supposed to add up to 400. So then I don't know if those are very, very different from each other. But we have two samples. So that's a big difference here. Maybe, maybe not. So two samples. Basically what that means is that we have two populations. That's a key distinction. So two populations and two samples from each of the, or one sample from each of those populations, so a total of two samples. So more than likely this is a test for homogeneity. Do these two populations look the same with regards to their agree versus disagree distribution? So there's only one variable, and that's whether or not they agree. So in this case, and I'm going to write this over to the side, that would be the test for homogeneity. Multiple samples, not just two, more than two even. One variable. So that way the data is two-dimensional. This is one-dimensional data because it's one variable, one sample. This is two-dimensional data. And the two dimensions are, well, the single variable, and that's going to vary by category. So there's going to be certain categories for the one variable. And then the other dimension varies by the sample in which we're talking about. So we can also think of that as a variable, but no, in this case, these are separate samples. So instead of what category you fall under, it's what group of people you were sampled from. So this is test for homogeneity. Two samples in this case, one variable. So chi-square, test for, handwriting kind of bad, homogeneity. Let's read the other pieces. So letter B, state the null and alternative. Oh crap, so I got to do that. So do not carry out a full test, so at least that's good. So, and then calculate the degrees of freedom. So this is A. B, I have to give hypotheses, which I might skip that. I'm not feeling the hypotheses today. So hopefully you're okay with that. So I'm not going to give the hypotheses. Maybe I can do that verbally. So in this case, we would state that the distribution of the responses, so whether or not they agree or disagree with the interview statement or the survey statement, is the same. So for the null hypothesis, is the same for whether the interviewer was a man or a woman. So you're talking about one variable and then for two different populations. So the distribution for men's responses, and that's agree versus disagree, with the statement that's given, is the same for when they're interviewed by a man and for when they're interviewed by a woman. So that's B. Letter C, degrees of freedom. In this case, you should be able to see that degrees of freedom is equal to 1. It's a 2 by 2 matrix. You subtract 1 for each of those numbers. So 2 minus 1 times 2 minus 1, 1 times 1 is 1. Should be that simple. And that's really all I want to concentrate on today. So we're just going to read a bunch of these and determine what type of test these are and then calculate degrees of freedom for each of these. So we'll look at number 2. The age distribution of the Canadian population and the age distribution of a random sample of 455 residents in the Indian community of Red Lake, that's Northwest Territories, are shown below. That's in Canada, I believe. Oh yeah, Canadian population, they already stated that. They're shown below. Based on U.S. Bureau of the Census, that's an international database, so based off of U.S. Census data, use a 5% level of significance to test the claim that the age distribution of the general Canadian population fits the age distribution of Red Lake Village. Okay, so it looks like U.S. Census data keeps track of this particular community, the Red Lake community. So what we're doing is we're checking the Canadian population distribution, and that's the age category. So how is age distributed amongst all Canadians? And then does the age distribution for those in Red Lake fit that particular distribution? Keyword fit. In this case, this is a goodness of fit test. And hopefully that's easy to see. So chi-square, this is goodness of fit. Now, this is bad practice if this were an AP exam. I would call this goodness of fit, in this case, test. So chi-square test for goodness of fit or chi-square goodness of fit test. Either or, doesn't matter. You don't want to just write GOF for short. You want to write out the words. You want to avoid using acronyms for the most part. So chi-square goodness of fit test for letter A. Letter B. So the null hypothesis, no difference between the age distribution for the population of community members in Red Lake and the population distribution for age for those in Canada, for all in Canada, that is. How do I calculate degrees of freedom? Degrees of freedom for a goodness of fit test is the number of categories for your one variable minus 1, in this case 3. So df is equal to 4 minus 1, which equals to 3. So there's only one variable, one population, so it's just the number of categories minus 1. Simple as that. Number 3. It is a common belief that more fatal car crashes occur on certain days of the week, such as Friday or Saturday, and that might be for obvious reasons and related to probably drunk driving. So those occur more often on Fridays and Saturdays. So let's see. A sample of motor vehicle deaths in Montana is randomly selected for a recent year. The number of fatalities for the different days of the week are listed below. Test the claim that accidents occur with equal frequency on the different days of the week. We had a problem like that was similar to this one under the goodness of fit one. So this is going to look like a goodness of fit. It's because we're going to assume that there's a uniform distribution of the day of the week. So each of those should be equally likely. So we would assume, or if you have a, actually no. So yeah, you would assume a uniform distribution. So there's 7 days of the week. So each of these would have a proportion of 1/7. Not 1/2, 1/7, all the way across. So then that's how you would calculate your expected counts. So in this case, this is goodness of fit. Does it fit a uniform distribution in this case? So chi-square, and I'm going to go ahead and write goodness of fit this way. Now that's bad, and I would suggest against it, but I'm trying to get through the video. So we'll deal with that. Degrees of freedom, pretty simple. Should be 6, 7 minus 1. So then just to check, does this fit the criteria for goodness of fit? Is it a single variable? Do we have a single sample from a single population? And the answer is yes for both. So one variable is the day of the week, and then it's just the one randomly selected set of car crash data. So we'll move on to the next one. This one's a two-way table, so most likely not goodness of fit. Suppose the researchers at a large university survey 200 randomly selected staff members. The staff members are asked about the kind of transportation that they used to get to work, as well as whether they are morning people or night people. Test the claim that mode of transportation is not, so that's is not, related to sleep tendency. Okay, so we're not actually testing the claim. We're checking to see what type of test I would use. So for part A, the type of chi-square test. So obviously chi-square, and which would it be? So what I would do is I'd look at how many samples they have. They have one sample, 200 people. So 200 people in a single sample. That is not homogeneity. Homogeneity is multiple samples, one variable. This is what we call the test for association or independence. Two samples, oh no, sorry. One sample, two variables. This makes for a two-dimensional data set. So one group of people or individuals, objects, whatever it is, one sample, and two variables, two survey questions, two measurements, whatever it is. Or if this were an experiment, that'd be two treatments. So one group of people split into two treatment groups. Possibly. So might need more information there. But anyway, so this is a chi-square test for association or independence. You could use either word, no big deal. Expected counts. This is the one where you count both dimensions. It's a 2 by 3. So 2 rows, 3 columns. So you subtract both of those numbers by 1, then you multiply, in which case you'd get 2. Degrees of freedom is equal to 3 minus 1, which is 2, times 2 minus 1, which is 1, 2 times 1, 2 degrees of freedom. Number 5. Everett, Price, Bettel, and Teljohan. So 1997. So that's probably a name of a article. So they mailed a survey to a random sample of physicians. Half were offered $1 if they would return the questionnaire. The other half served as a control group. So is there a big difference between being offered $1 to return a questionnaire and not being offered $1? So I think that's what they mean by control group. That's kind of weird. They probably should have upped the amount here. But anyway, using the results below, does the incentive produce the same results as the control? So incentive group versus control group. So this is probably where we start getting we'd have to get a little philosophical about it. Which route do we take? Because it's more than likely not a goodness of fit test, but then we can probably argue which of the other two types would it be, association or homogeneity. So, and the reason why, because when you take two treatment groups, a lot of the times it's a split between people from the same sample. So a lot of the times there's one sample, you split that sample into two groups, preferably randomly, and then you give one of the groups one of the treatments, and you give the other group the other treatment. So you can argue that this is a test for homogeneity. Actually, no. One sample would mean that it's a association. So you can argue it's a test for an association. Because association tests happen for single sample data. So data for one sample, and then there's only two variables. So the variable would be, well, which of the two treatment groups that they were in versus what the outcome was. I think that's the outcome. The response variable. Yeah, the outcome in this case, they returned it and completed it. Returned it, but uncompleted or incomplete. There was no response or undeliverable, which I don't know how they would determine the difference between a no response and an undeliverable situation. Or they probably made an attempt to deliver it, and there was a failure at delivery. So we can say it's association because it's one group of people, two variables, and one of the variables happens to be which treatment group they were placed in. So we can box that association. You can also argue that these are two different populations. It's kind of hard to do that though for this situation, since one of those variables is whether or not they got the incentive, not necessarily two different groups of people. So yeah, we would go with association. So I'd probably stick by association and defend that one a little bit better than defending the situation where it's a homogeneity test. So I'd go with association. Okay, the easier question, degrees of freedom. There are 4 categories for one of them, so multiplying 3, and 2 categories for the other, multiplying 1. In this case, 3 times 1 is 3. So it's a 4 by 2 or a 2 by 4. You subtract 1 for each of those numbers. 1 times 3 would give you 3. Okay, so what next? Number 6, and I think that's the last one. Canada has a universal healthcare system. The United States does not have a universal healthcare system, but let's see, often offers more elaborate treatment to patients with access. How do the two systems compare in treating heart attacks? So that's the main question. So what are the actual outcomes of medical situations? And that's very complex too, because population-wise, we're very, very different with regards to what pre-existing conditions we have. Researchers compared random samples of 260 US and 400 Canadian heart attack patients. One key outcome was the patient's own assessment of their quality of life relative to what it had been before the heart attack. So here are the data for the patients who survived a year. So those who survived a year's time after the occurrence of the heart attack. So these are only people who survived. And then they state what their quality of life was before that heart attack happened. And this is going to be for 2 different populations. So the key thing here, there are 2 random samples. A random sample of 260 US, 400 Canadians. Because it's 2 samples, this is going to be a test for homogeneity. Again, homogeneity is not limited to 2 samples only. It could be for more than 2 different groups. So they could have also included Mexico in this and maybe other countries. And the reason why I said Mexico, because that's North America. So, so a test for homogeneity, because it's multiple samples and it's 1 variable, quality of life in this situation. Then how would I calculate degrees of freedom? Same as always. How many categories, by the way? 1, 2, 3, 4, 5. So that would be 4, because there's 2 populations. So degrees of freedom is 4 times 1. And that's going to be it for this particular handout and for Unit 10 also. This was the end of Unit 10. So you're going to have a homework assignment, which will cover everything that I covered in the videos for 10.4, 10.5, and this one, 10.6. This one's 10.6, by the way. Now, in addition to that, I'm going to probably be giving you guys a video for each of 2 AP free response questions, maybe 3. And that's going to be 2. So at most 2. I'm not going to do more than that. So it'll just be 2. If anything, there's going to be 1 at least. So, but I might go with 2. And it's going to be over an AP free response question. What I'll probably do is do something similar to what I normally do in class at the end of the first or second half of a unit. So when we reach the halfway point or at the end of a unit, we normally do an AP free response question in class. I time you guys 13 minutes. You respond, and then we grade them together. So what I'm probably going to do is I'm going to give you a video containing 1 free response question. I'll give you instructions to pause the video to take or to respond to the question, 13-minute timer or a 15-minute timer, because I normally extend it to 15 minutes anyway, and then I'll extend it even further if we need extra time. So take about 15 minutes and then unpause the video for the grading for that. And this won't be for a grade, so I'm not going to be using whatever your responses are for a grade, so don't worry about grading. What you want to use this for is AP free response practice, which is extremely important because that test is coming up in about a month's time, about 5-6 weeks time. So I think our test is on, I don't remember the date. So more information on that later, probably in the next video that I have prepared with that AP free response question. And there's going to be more videos to come. And the reason being is because there's going to be another unit. So there's Unit 11 over linear regression t-testing. So there's going to be inference procedures for linear regression. And then we're going to have some review videos. So I'm going to want to review all the major topics with you guys again. And I'll be giving you guys more opportunities to practice the AP free response stuff. So there'll be videos per free response problem. So there'll be a lot more videos to come. So please be expecting those. We won't be having a test for this unit since MHS isn't, they're suggesting that we don't give tests, because that's kind of hard anyway for me to grade tests and stuff like that. So I'm pretty sure for for the remainder of this 6 weeks, while we're still under like lockdown for the COVID-19 situation, it's going to be one minimum assignment, and it's going to be a minor assignment a week. No major assessments are required. So the way I'm taking that is I'm not going to give any tests at all. So I'd rather not bother with testing. Okay, so we'll go ahead and stop here. Expect more videos to come, especially for this unit and then for the future unit, Unit 11.